Hello viewers, welcome to online course on Mathematics 3. This course basically for undergraduate student or BTech student of engineering field. Today we are going to discuss about the Coset and Lagrange's theorem. On the chapter of group theory in the module algebraic structure. Myself Sanjay Vishwas, Assistant Professor of Mathematics, Department of Applied Science and Humanities of Guru Nanak Institute of Technology. Here is my details of contact information. If you have facing any kind of problem regarding my online class, you can call me or send message through my mail ID. So before we start today's lecture, let's quickly recall in the last lecture. So in the last lecture we have discussed about the cyclic group in the module algebraic structure. So in this lecture we have discussed about the definition of a cyclic group and some related examples on cyclic group and some theorem on cyclic group we have discussed in the last lecture. Today we are going to discuss about the Coset and Lagrange's theorem. This is my fifth lecture on algebraic structure. Here is the content of today's lecture. So at first we will discuss about the definition of a coset, and after that we will talk about the theorem on coset, and there are some theorem which are related to coset we will discuss in this lecture, and after that we will talk about the Lagrange's theorem as well, and this is the theorem on coset and some related examples we will discuss in lecture 5, that means in today's lecture. At first we will begin with the definition of coset, and you know there are two coset, right coset and left coset. So here is the definition. Let H be a subgroup of a group G. So you know H satisfy all the properties of a group and H is a subset of G, then H is a subgroup of G. Also let A be an element of G. Then the subset HA, so this is the subset such that H belongs to H, where H be the element and A be the element of G and H be the element of H. Therefore H into A, small h, where small h is the element of capital H, is called a right coset of H in G and is denoted by capital H into A, where capital H is the subset of G and small a is the element of G. Thus HA is equals to H into A such that H is belongs to H and A is belongs to G is called the right coset. Similarly, the left coset of H in G and is denoted by AH and is defined as A into H, where A be the element in G and small h is the element in H, so that H is belongs to H, and this is called the left coset of H in G. So there are two types of coset, left coset as well as right coset, and left coset is denoted by AH and right coset it is denoted by H, where H is a subset of G and small a is the element of G. And there are some note on right coset as well as left coset. So the first one, since H into E, where E be the identity element of G and it is equals to H, and H is equal to E into H, that means H into E is equal to H is equal to E into H. So H itself a right as well as left coset of H. And the second note on right coset or left coset, that means the coset, and is since H is a subgroup of G, and so E is belongs to H, where E is the element and E is the identity element in H, and E into A, where A is the element in G. So E into A, and it is equals to, from the definition of the right coset, it is equals to A, and A is belongs to H into A. Thus, if HA is any right coset, then at least one element A is belongs to H into A. So consequently, every right coset is non-empty. Similarly, every left coset is non-empty. And after that, we will take one more point on coset. When G is an abelian group, then AH is equal to HA for all H belongs to H, where A be an element in G, and hence the right coset HA is equal to the corresponding left coset AH. Okay, so when G is an abelian group, then HA and AH both are equal. But if the group G is not abelian, then we may have AH is equal to HA or AH not equals to HA. So when G be an abelian group, then left coset and right coset both are equal. But when G is not an abelian group, then from this we cannot say AH is equal to HA or AH is not equals to HA. So it is either AH is equal to HA or AH not equals to HA. Okay. This is the third properties of right coset as well as left coset. And after that, we'll take an example on the coset. Consider the additive group of integer z plus. Okay, so where z is the integer and plus is the binary operation. Where z is equal to, so the elements of z are 0, plus minus 1, plus minus 2, plus minus 3, and up to infinity. And h is a subset of z, and let h is equal to 3 into z, so multiple of 3 of integer, and the elements of 3z, they are 0, plus minus 3, plus minus 6, plus minus 9, and up to infinity. So in that case there are infinite number of elements as well. But z is a proper subset of 3z, that means 3z is a subset of z. So let us form the right coset of H in Z plus as given below, and you know that 0 is an element in G, and H is equal to, you know that H is equal to H plus 0. So H plus 0, it is equals, and you know that H is a subset of a set Z, and the elements of H are 0, plus minus 3, plus minus 6, plus minus 9, and up to infinity. So H plus 0, it is equals to H as well, and the elements of H plus 0, they are 0, plus minus 3, plus minus 6, plus minus 9, and up to infinity. And after that we will take 1 is the element, is belongs to G, then H plus 1, that means 1 plus 0. So you know that H is the set, the infinite set, for the infinite number of elements. Now added by 1 on that set, then all the elements will be changed, and they are 1 plus 0, 1 plus minus 3, 1 plus minus 6, 1 plus minus 9, and up to infinity. So therefore, after simplifying this, we'll get the elements of H plus 1, and it will be minus infinity to minus 5, minus 2, 1, 4, 7, and up to infinity. Similarly, we will find H plus 2 when 2 is belongs to G, and in that case where all the elements of H are added by 2, that means 2 plus 0, 2 plus minus 3, 2 plus minus 6, 2 plus minus 9, and up to infinity. and after simplifying these numbers, that means the elements, we'll get minus infinity to minus 4, minus 1, 2, 5, 8, and up to infinity. So they are all the elements of H plus 2, where 2 is belongs to G. Similarly, we will find the coset, that means H plus 3, where 3 is belongs to G. So therefore H plus 3, and the elements of H plus 3, they are 3 plus 0, 3 plus minus 3, 3 plus minus 6, okay, and 3 plus minus 9 as well, and up to infinity. And after simplifying this, we'll get 0 plus minus 3 plus minus 6 plus minus 9 and up to infinity, and it is equals to, the given subset, that means capital H. Okay, so H is equals to H plus 3. Similarly, we will find H plus 4, and you know that after simplifying this result, we will get H plus 4, and H plus 4 is equal to H plus 1. So elements of H plus 4 are equal to the element of H plus 1. As well, H plus 3, the elements of H plus 3 is equals to the elements of H plus 2. Therefore, H plus 3 is equals to H plus 2. And again, we will take minus 1 is belongs to G. So therefore, the right coset H plus minus 1, it is equals to H plus 2. That means all the elements of H plus minus 1, it is equals to the elements of H plus 2. And H plus minus 2, this is also the right coset, where minus 2 is the element in G. So H plus minus 2, it is equals to the coset H plus 1. That means all the elements of H plus minus 2, it is equals to all the elements of H plus 1, and so on. So thus we get only 3 distinct right coset, and they are H, H plus 1 and H plus 2. And H plus 3 is same as H plus 4 is same as H plus 1, H plus 5 is same as H plus 2 as well. So therefore there are only 3 distinct right coset, and they are H, H plus 1 and H plus 2. So obviously Z is equal to H union H plus 1 union H plus 2. So in that case, where these 3 elements, that means 3 right coset, they are distinct. So obviously we can write Z equals to H union H plus 1 union H plus 2. So after that we will take some theorem on coset. So this is the first theorem on the coset. If H is any subgroup of a group G and H is belongs to H, then H into H is equal to H is equal to small h into capital H, where small h is the element in capital H. Alright, capital H is a subgroup of G. So here is the proof of the theorem 1. So let small h, that means the element, and within capital H, and H into H1 be an arbitrary element of H into H. So where capital H is the subgroup of a group G. So then H1, small h1 is belongs to capital H by the definition of the left coset. Okay. So since H is a subgroup and H comma H1, that means small h comma small h1 is belongs to capital H, then every element of H into H, that means the left coset of H, is an element of capital H. So from this we conclude that small h into capital H, that means the left coset of H, it is the subset of capital H, and we can write in equation number 1. Again let small h1 is belongs to capital H, where small h1 is the element, arbitrary element in H, capital H, where H is a subgroup of G. So now H1, and it can be written as H into H inverse. So you know that H into H inverse is the identity. So identity element into H1 is equal to H1. Okay. So H can be written as H into H inverse into H1. So now applying the associative property, where capital H is a subgroup, so H satisfies the associative property as well. So after applying the associative property, we will get H into H inverse into H1, where H is belongs to capital H, and this implies H inverse is also belongs to capital H. Since capital H is a group, so H satisfies the inverse property as well. So if small h belongs to capital H, then H inverse is also belongs to H. Then H1 comma H inverse is belongs to H. This implies H inverse into H1 belongs to capital H. So this is the theorem on subset. I have already proved in the previous class. So from this we have seen that H into H inverse into H1, it is belongs to H into H, where H inverse H1 is belongs to capital H. Okay, so where H is the subgroup of G. So H1 is belongs to H, and this implies H1 is belongs to H into capital H. So thus for every element H1 belongs to H, it is the element of H into H. So thus H is subset of H into H, and we can write it equation number 2. So from equation 1 and 2 we conclude that H into H is equal to H. And similarly we can prove that H, that means capital H into small h, it is equals to capital H. So combining these two, we will get H into H is equal to H is equal to small h into capital H. So hence the proof of the first theorem on coset. So after that we will take the second theorem on coset. So here is the theorem. Let H, capital H, be a subgroup of a group G, and let AB be two elements of G. Then A into H is equal to B into H if and only A inverse B belongs to H. And the second one, H into A is equal to H into B if and only B A inverse belongs to H, where H is the subgroup of G and AB be two elements in G. So here is the proof of the above theorem. This is a very important theorem for coset. And applying this theorem, we will found some solution of the typical examples. And as well, we will prove some theorem applying this result as well. So here is the proof of the theorem 2. So I will start with the first part of the above theorem. So let AH is equal to BH. Okay, this is given. So from this we shall prove that A inverse B belongs to H. Let AH is equal to BH, then for some H1 comma H2 is belongs to H, where H1 and H2 be two elements in capital H, and therefore AH1, okay, where H1 is belongs to H, and it is equals to BH2, where H2 is also belongs to H. And this equation implies, after simplifying, AB inverse, okay, and it is equals to H1 H2 inverse. But H1 H2 belongs to H, and H is a subgroup of G, so H1 H2 inverse it is belongs to H, and this is the one of the property of a subgroup. And I have already proved that theorem in the previous lecture. So H1 into H2 inverse it is belongs to H, as H is a subgroup of G. So therefore A inverse B, and it is belongs to capital H. And conversely, this is the sufficient part of the first part of the above theorem. So conversely, let A inverse B belongs to H, and from this we shall prove that AH is equal to BH, where A and B be two elements in G. So then A inverse BH is equal to capital H. So you know that if H is belongs to H, so H is the element in capital H, then H into H it is equal to H by theorem 1. And applying this theorem 1, we conclude that A inverse BH is equal to H. So therefore, taking A on left on both sides of this equation, we get A inverse BH is equal to AH, and you know that A inverse is equal to E, where H is a group as well and it is a subgroup of G, so A inverse is equal to E, okay, where E is the identity element. So E into BH it is equals to AH, and from this we conclude that BH is equal to AH. Hence the proof of the sufficient part of the theorem 2. So AH, that means AH is equal to BH if A inverse B belongs to H. Okay. So hence the proof of the second theorem of Coset. So similarly we will prove that the second part of the above theorem, that means HA is equal to HB if and only B inverse belongs to H. So we will continue our discussion on the theorem on coset, and after that we will take the third theorem on coset. So here is the theorem. Any two right or left coset of a subgroup are either disjoint or identical. Here is the proof. Let H be a subgroup of a group G, and AH and BH both are the right coset of H in G. Suppose HA and HB are not disjoint. That is, HA intersection HB is not equals to phi. So there exists at least one element in HA intersection HB. Let X be the element and it is lies in HA intersection HB. That means X is belongs to HA and X is belongs to HB. So now let X is equal to H1A and X is equal to H2B. So in that case, where if X belongs to HA, and from this we will get X is equal to H1A, and from the second part, that means X belongs to HB, and from this we will get X is equal to H2B, where H1 and H2 be two elements in capital H. So therefore, from the above two equation, we conclude that H1A is equal to H2B, and this implies BA inverse is equal to H2 inverse into H1. So, and you know that H1, H2, two elements in H, and H is a subgroup of G. So H2 inverse H1 it is belongs to H. Therefore, B inverse is belongs to H, and it's implied HA is equal to HB. Applying the second theorem on coset, and I have already discussed in the previous slide. So therefore, the two right cosets are identical if they are disjoint. Thus either HA intersection HB is equal to phi or HA is equal to HB. Similarly, we can prove that either AH intersection BH is equal to phi or AH is equal to BH. That means this theorem is also applicable for two left coset as well. That means AH intersection BH is equal to phi or AH is equal to BH, where A, B, B two elements in G. So after that we will take one more theorem on coset, that means the theorem number 4. Let capital H be a subgroup of a group G, then there is a one-to-one correspondence between any two right or left coset of H in G. Here is the proof. Let HA and HB be any two right coset of H in G, where AB be two elements in G. So let us define the mapping Okay, there is a mapping F and such that HA to HB. Okay, where HA and HB to right coset in G. By F of HA is equal to HB. So there is a relation, that is the mapping from HA to HB, and defined by F of HA is equal to HB for all H belongs to H. So now let two elements, say H1A and H2B, it is belongs to HA, where H1 and H2 belongs to H, and A, B any elements in G. So then from the above relation, that means F of HA is equal to HB, and from this relation we will get F of H1A, it is equals to H1B, and F of H2A, and it is also equals to H2B. Now F of H1A is equal to F of H2A, so from this we will get H1B is equal to H2B, that means H1 is equal to H2. By the right cancellation law we will get this one. So this implies H1B is equal to H2B. So F is 1 1. Again let H3B be any arbitrary element of HB. That means on the codomain, on the mapping F such that HA to HB. So H3B any arbitrary element in HB. So from this we shall prove that F is onto. So then H3B is belongs to HB, and this implies H3 is belongs to H. And you know that H3 is belongs to H, and this implies H3A it is also belongs to HA, where H is the right coset of H in G. So now F of H3A, so applying the above relation, that means F of HA is equal to HB. So we conclude that F of H3A and it is equals to H3B. So thus H3B is belongs to HB, and this implies there exists an element H3A belongs to HA such that F of H3A is equal to H3B. So F is onto. This is the definition of the onto mapping. You know that. Hence the result. So similarly, we can show that there is a one-to-one correspondence between any two left coset of H in G. So after that we will take one more theorem on the coset, and there is a note on the above theorem. Since H itself is a right as well as left coset, so the number of elements in any coset, that means in right coset or left coset of H in G, is equal to the number of elements in H, that is order of H. Hence order of HA is equal to order of HB is equal to order of H. Okay, and after that we will take the fifth theorem on coset. So let H be a subgroup of a group G, then there is a one-to-one correspondence between the set of left and the set of right coset of H in G. This is the similar theorem as theorem 4. So here is the proof of the fifth theorem. Let U and B denote the set of left and right coset of H in G respectively. So let us define a mapping from U to V, where U is the domain and V is the codomain. That means U is a left coset in that case, and V is the right coset of H in G. And by the relation F of H is equal to HA inverse for all A belongs to G, and AH is belongs to U. Okay, so H is the left coset and it is belongs to U. So obviously HA inverse is the right coset, and hence HA inverse is belongs to B. So we have AH is equal to BH, and from the previous theorem we have A inverse B, it is belongs to H, and this implies, you know, that B inverse of inverse it is equals to B. So this relation is implies A inverse into B inverse of inverse, it is also belongs to H. That means H A inverse, it is equals to H B inverse. By applying the second theorem on coset, we will get this one. So this implies f of AH is equal to f of BH. That means H A inverse is equal to f of H. So applying the above relation, then from the last equation we will get f of H is equal to f of BH. Therefore f is well defined function. So now f of H is equal to f of BH, and this implies that f of H is equal to HA inverse and f of BH is equal to HB inverse. Okay, so from this equation we conclude that A inverse into B inverse of inverse, it belongs to H. Applying the second theorem on coset, we have found this one. That means A inverse into B inverse of inverse, this belongs to H. So therefore f is 1 1. Next, let HA be any arbitrary element of V. That means we shall prove that the function f is onto. So HA be any arbitrary element of V, that means in the codomain set, and V is actually the right coset of H in G. So then A inverse H belongs to U, where U is the left coset, and this is actually the domain. And applying the above relation, that means f of H is equal to HA inverse. So then from this relation we will get f of A inverse H is equal to H into A inverse of inverse, that means HA. So therefore HA belongs to V. So HA be the element in the codomain set of the mapping F such that U to V, where U is the left coset and V is the right coset. Okay, so this implies there exists an element A inverse H. Okay, so A inverse H, it is belongs to U, that means in the domain set, such that f of A inverse H is equal to HA. So f is onto. So hence the result. So f is a 1 1 as well as f is onto. So there is a note. So from the above theorem we conclude that the number of distinct right coset of H in G is equal to the number of distinct left coset of H in G. That is, order of HA is equal to order of HB. So that means the function f is a bijective, that is 1 1 and 1 2. So order of left coset as well as the order of right coset are equal. Now we will move on the next part of the lecture, that means index of a subgroup. So here is the definition of index of a subgroup. Let H be a subgroup of a group G, then the number of distinct right coset of H in G is called the index of H in G and is denoted by G such that H within third bracket, or Ig of H. I, where G is the in suffix of I of H. Okay, this is actually the index of H in G. And after that we will discuss about the Lagrange's theorem. So this is the theorem number 6 as well, and the definition of the Lagrange's theorem. And here is the definition. The order of each subgroup of a finite group is a divisor of the order of a group. This is the very important theorem, or the Lagrange's theorem on group. So here is the proof of the above theorem. Let H be a subgroup of a finite group G. Also let order of G is equal to n and order of H is equal to m. So order of G and order of H are distinct. And let H, so H be the subset of G, and H is also the subgroup of G. So H contains the elements H1, H2 up to Hm. So order of H is equal to m. So there are m distinct elements, and they are H1, H2 and up to Hm. So then each right coset HA for all A belongs to G has m distinct elements, and they are H1A, H2A and up to HMA. As you know, HIA is equal to HJA, and this implies hi is equal to he by the right cancellation law. And since G is a finite, then the number of distinct right coset as well as left coset of H in G, then these right coset are distinct, and hence G is equal to HA1 union HA2 and up to union HAK. So G is a finite set in that case. A number of right coset as well as number of left coset of H in G, they are distinct, and it is equals to capital G. That means G is equal to HA1 union HA2 and up to HAK. And where HA1 is the right coset and order of HA1 is M, because HA1 is the right coset has M distinct elements, so order of H1 is equal to M as well as order of HA2 is equal to M and up to HAK is equal to M. So from this we conclude that order of G it is equals to order of HA1 plus order of HA2 and up to order of HAK. And you know that order of HA1 it is equals to M, order of HA2 is equal to M, and up to order of HAK and it is also equals to M. So order of G is equal to M plus and up to K times. So there are k number of right coset as well as k number of left coset. So and each coset, that means each right coset or left coset has M elements. So therefore order of G it is equals to k into M, but order of n it is equals to n, so n is equal to k into M. So from this we conclude that k is equal to n by M. So where n is the order of G and M is the order of H, therefore order of H is a divisor of order of G. This is the proof of the Lagrange's theorem. So there are some note on the Lagrange's theorem. The index of H in G it is equals to order of G by order of H. And after that we will take second note. It is actually if G is a group of prime order P, then G can have no proper subgroup. And the third note, it will be the converse of the above theorem is not true. For example, the alternative group A4 is of order 12, but there is no subgroup of A4 of order 6 through 6 is a divisor of 12. So alternative group is not satisfy the converse of the Lagrange's theorem. So after that we will take some more theorem on the Lagrange's theorem. So here is the theorem, that means the seventh theorem on coset. Every group of prime order is cyclic. So here is the proof of the above theorem. Let G be a group of prime order P, and since P is a prime, so order of G is greater than 1. Okay, so 1 is not a prime, and hence G has an element A and A is not equals to E. And let H be a cyclic subgroup generated by A, then order of H is also greater than 1. And A, you know that A is not equals to E, and E is the identity element. So order of A, that means order of H, it is also greater than 1. So by the Lagrange's theorem, you know that order of H is a divisor of P, but P is a prime number, so therefore order of H is equals to P. Hence H is equal to G. This shows that G is a cyclic group. And after that we will take one more theorem on the Lagrange's theorem. So let G be a group of finite order n and A be an element in G, then order of A is divides n and A to the power n is equal to E. So here is the proof of the above theorem. Let H be a cyclic subgroup generated by A, and then by the Lagrange's theorem order of H is a divisor of order of G. That means n, so you know that order of G is equal to n, but order of A is equal to order of G, so consequently order of A is a divisor of n. And let order of A is equal to m, then n is equal to m into k for some integer k. And now a to the power m is equal to e, and hence a to the power n, and it is equals to a to the power m to k, where a to the power m is equal to e. So from this we will get e to the power k, and e to the power k is equal to e. So you know that any power of the identity element, it is equals to identity. So a to the power m is equal to e. Hence the proof of the above theorem. Now move on the next theorem. So this is actually the format theorem of Coset. So if p is a prime number and a be any integer, then a to the power p is identical equals to a modulo p. So here is the proof of the theorem, that means the format theorem. Let G be a set of all non-zero residue classes of integer modulo p. Then G form a group of order p minus 1 with respect to the multiplication of residue classes. As p is a prime, then the identity element of this group is 1. So 1 is the residue classes. So there are two cases, if p is a divisor of a or p is not a divisor of a. So if p is a divisor of a, then the residue classes a, it is equals to 0, and so the residue classes a is not belongs to G. So but p divised a implies p divised a to the power p as well, and from this we will get p divised a to the power p minus a, it is identical equals to a modulo p. And the second case of the above theorem, it is when p is not a divisor of a, then the residue classes a, it is not equals to 0, and so a residue classes a is belongs to G. Hence by the above theorem, that means the theorem number 8, we conclude that a to the power p, that is the residue classes a to the power p minus 1, it is equals to 1, and this implies a to the power p minus 1, the residue classes a to the power p minus 1, it is equals to 1. So from this we will get this one, that means a to the power p minus 1 is identical equals to 1 is modulo p. So therefore p divised a to the power p minus 1 minus 1, and this implies p divised a into a to the power p minus 1 minus 1. That means after multiple by a on the denominator, we will get p divised a to the power p minus a. So that is a to the power p is identical equals to a modulo p. So in both cases we conclude that if p is a prime number and a be any integer, then a to the power p is identical equals to a modulo p. This is the proof of the format theorem. So after that we will take one more properties of the coset. Let H1 and H2 be a finite subgroup of a group G, then the order of product of two subgroups H1 and H2, that is order of H1 H2, it is equals to order of H1 into order of H2 divided by order of H1 intersection H2. Okay, this is the properties of the Lagrange's theorem, or product of two subgroups H1 and H2. So after that we will take some more examples on the coset as well as the Lagrange's theorem. There is the first problem. So that HA inverse is equal to A inverse H for all A belongs to G, where H is a subgroup of G. So here is the solution. Let HA inverse is belongs to HA inverse, be arbitrary. So then HA is belongs to capital H into A. So capital HA is the right coset of H in G, where H is belongs to H, and you know A inverse H inverse, it is belongs to HA inverse. But H is belongs to H implies H inverse is also belongs to H. You know that H is a subgroup of G, so H is also a group. So H is itself a group, so it satisfies the inverse property as well. So if H is belongs to H, then H inverse is also belongs to H. So therefore A inverse H inverse, it is belongs to A inverse H. And you know that A inverse H inverse, it is equals to HA inverse, and it is belongs to A inverse H. So therefore HA inverse is subset of A inverse H, and we can write it equation number 1. Next let A inverse H, so A is the element in G and H is the element in H. So A inverse H is belongs to A inverse H, be arbitrary. Okay, so this is actually the element of A inverse H. Then A inverse H, it is equals to A inverse into H inverse of inverse, where you know H is equal to H inverse of inverse. So therefore, this term can be written as H inverse of A whole inverse. So this is the properties of the inverse function, and it is belongs to H A inverse. So you know that H inverse H is belongs to H A. So H inverse A whole inverse, it is belongs to H A inverse. As H inverse belongs to H, as so H A inverse H is belongs to H A. So therefore, A inverse H is subset of H A inverse, and we can write it equation number 2. So from equation 1 and 2 we conclude that H A inverse is equal to A inverse H for all A belongs to G. This is the proof of the first example of coset. So after that we will take the second example. Let H be a subgroup of a group G and define S is equal to X belongs to G such that XH is equal to HX. So prove that S is a subgroup of G. So here is the solution. Let x1 and x2 be two elements in H, then x1h is equal to hx1. Applying the above properties of the given problem, as well as x2h is equal to hx2. So first we shall show that x2 inverse it is belongs to S. So we have x2h is equal to hx2, and it is implies x2 inverse into x2h into x2 inverse. So in that case we'll take x2 inverse, or we operate x2 inverse on left as well as on right, on the both side. We'll get x2 inverse into x2h into x2 inverse, it is equals to x2 inverse h x2 into x2 inverse. So now applying the associative property on the group, and you know that H is a subgroup of G and H is also a group, that means H is itself a group. So therefore x2 inverse x2 into h x2 inverse, it is equals to x2 inverse h into x2 into x2 inverse. Okay, so and you know that H is a group, so and x2 and x2 inverse both the elements are in H. So x2 inverse into x2 it is belongs to H, and you know that x2 inverse x2 it is equals to E. So E into H x2 inverse, so this is the inverse function, and you know the x2 inverse is equal to x2 is equal to E. What is the identity element? Into H into x2 inverse, it is equals to x2 inverse H into E. Okay, so from this we conclude that H into x2 inverse it is equals to x2 inverse into H. So therefore x2 inverse it is belongs to S. Now we shall show that x1 into x2 inverse it is also belongs to S. Then we conclude that S is a subgroup of G. So we have x1 x2 inverse of H. So this is equals to, you know, applying the associative property, and then from this we will get x1 into x2 inverse of H, and x2 inverse of H it is equals to, you know, that H x2 inverse. So you know x2 inverse is belongs to S, then x2 inverse H is equal to H x2 inverse. Okay, applying the above relation we'll get this one. So from this we'll get x1 H x2 inverse, it is equals to H x1 into x2 inverse. So again applying the associative property, then from the last relation we'll get x1 x2 inverse of H, it is equals to H into x1 x2 inverse. Therefore x1 x2 inverse it is belongs to H. So thus x1 x2 belongs to S, it is implies x1 x2 inverse it is also belongs to S. Hence S is a subgroup of G. Hence the proof of the second example on coset. So after that we are move on the third example on coset. So here is the example. So that every proper subgroup of a group of order 6 is cyclic. So here is the solution. Let G be a group of order 6 and H be a proper subgroup of G, then order of H is a divisor of 6 by the Lagrange's theorem. So you know that order of H is a divisor of 6. That means order of G. So but the divisor of 6 and they are 1, 2, 3 and 6. And since H is a proper subgroup of G, so order of H is not equals to 6. So it is less than 6. So if either order of H is 1 or order of H is 2 or order of H is 3. So if order of H is 1, then H is equal to identity element. So H is equal to E. So which is a cyclic group. And if order of H is equal to 2, then H is cyclic, as the group of prime order is cyclic, you know that. And if order of H is equal to C, then it is also cyclic. So H is a cyclic as 3 is a prime. And a group of prime order is cyclic. So thus every proper subgroup of such a group is cyclic. That means the every proper subgroup of order of a group 6 is cyclic. So hence the proof of the third example of coset. So I will stop here today's lecture. Thank you.